This is homework 2, part 1, the collaboratory edition. I know this is not the ideal camera angle. I apologize about that. I just do not have a detachable keyboard yet. Once I get one, I do have one ordered. Once it arrives, I will be able to do the proper camera angle. But just for reference, I am just using my tablet, which I have mirrored to the screen so you can see everything that's going on, and nothing is in my surroundings. Guess you just have to take my word for it this time, but next time I will have the proper recording layout. So yeah, this is my tablet. Alright, so as you can see, I already imported our base code, our import numpy, which is numerical Python, our integrate tool, and our subplot tool. I also already put in our constants, or our variables. Gravity, initial height, height of the tank, rho of water, density of water, cross-sectional area, and the area of the hole. So what the whole problem is for this problem is defining the deriving the differential equation for solving the height of the water in the tank as a function of time. So we figured that out. I already wrote on it, but we already figured that out. So we're going to plug that into Python. We're going to call it the right-hand side of the equation. It's a function of time and y. H is equal to y, which is a vector. We also need to put in the velocity function, since that is an entire debacle. We need to put that in. So that is going to be equal to, we're going to throw in, since it is a square root, we're going to use numpy square root, numerical Python square root, and then later on in coding this problem, you come to find that if you don't use absolute value, it won't work, because eventually the values inside of the square root will go negative and it will spit an error at you. So we're just going to put in numpy absolute value to begin with. So 2 times everything inside. So that's 2 times 1 over rho times 101325, and then 10325 times height of the tank minus the initial height divided by height of the tank minus the height of the water at any given time. That is also minus 1 multiplied by, nope, not multiplied by, plus gravity times the height of the water. Make sure all of these are accounted for. This is an extra. Or do I need this one? I do need that one. Then we need to define the function, dHdt, and that is equal to the negative area of the hole times velocity squared, v2, velocity exiting the tank, over the cross-sectional area. And we know that because it is right here. Then we want to return dHdt, but we need that in a matrix. Why is it not full? Oh, because I had it uppercase. That is why. Everything is case sensitive. Drives me crazy. because I'm not very good at this stuff. There it is. No errors. Perfect. Alright. Now, before I even go and graph it, we're just going to get this out of the way, make this a nice and short video. When you go to graph it and you don't set bounds, it will split out, since we had an absolute value, the from 100 to 0 and from 0 to 100. We don't want that. We just want from water to no water, not from no water to water. So we need to define a bound so that when the water level goes to 0, the function stops. So we're going to do that. We're using pretty much the same thing that we just did. Except our V2 now is just going to be this right there. Huh? Oh my goodness. Oh my goodness. I don't know all that. What just happened? V2 is equal to... Oh no, it deleted. Oh. Alright, it's alright. We can type it again. I'll cut this out of the video. I'm typing it again. What else do we? We need to return V2. And then to set the bound, it is V20 underscore events dot terminate equal to true. Perfect. Now we are going to solve the integral, which is the right hand side, our bound 0 to 10, our starting here, the initial height. Our method is going to be redow, because that's what it always is. Our dense output is going to be true. And the event we just added that terminates when water level 0 is equal to V20 underscore event. Right? Yes. Alright, I restarted my runtime, played around with it a little bit, finally got it to work. So there's that. It splits us out our events. Now we need to plot it. So we need to import our plotting commands, and I will do that right now. Alright, so our x value is going to be tplot, and our y value is going to be, we need to give this a name. We're going to give this the resultant. I think I might need to add a little bit more of that in a second. We need to give this linspace some values and put in the terminal here. So res.t underscore events. That is going to be, I have to put 2 of these in here. That'll be 500. That's just the linearly spaced points it adds. And then I think I throw one of these in here. It should be good. Yeah, this is very finicky. I kind of forget. I forget the command I need to use, but I need to put this. I basically need to put the terminal into here so that this knows. Hold on, let me figure it out. It's supposed to be event. It's supposed to be event. Let's try events. Alright, that's good. Now it doesn't like this. I think there's more to this. So there we go. Alright. So here is the function of the water level with respect to time. And notice how when the water level goes down, it doesn't go past 0. So thank you very much. There is the answer.